Hello. This video includes information on free energy and equilibrium.
We're going to kind of look at that delta G value from our thermochemistry chapter. And when we talk about free energy, we were looking at it under standard conditions. Well, now we're going to switch that a little bit. The free energy change for a process taking place when the reactants and the products are not at standard conditions, meaning they're either not 1 ATM or they're not 1 molar. We can relate that by looking at this equation here. So this little not sign here tells us that the values are at standard conditions. Okay, 1 ATM, 1 molar concentrations. This value here means we're not at standard conditions. And if we look, we have a Q here, which is not equilibrium values. So we're going to relate K and Q and delta G. We want to calculate the delta G value, the free energy change, at 875 degrees Celsius in a 5-liter container containing 0.100 moles of all 3 of these gases. Now, it tells us that at standard conditions, that value would be 33 kilojoules per mole. But that would be when these concentrations are 1 molar. They're not 1 molar. So we're going to have to figure out the concentrations, figure out Q, and then calculate our new delta G value. The delta G at standard conditions is what we were given. Okay, now we were given it in terms of kilojoules per mole. But the R value we're going to use is in terms of joules per mole Kelvin. So we're just going to do a conversion from kilojoules per mole to joules per mole. And we're going to do that by just multiplying by 1,000. So here's our free energy at standard conditions. We were given that number. We're going to add to that R, which is 8.314 joules per mole Kelvin. This is a constant, times our temperature, which has to be in Kelvin. So we're going to add 273 to 875. And then we're going to take the ln of Q. Now, Q is products over reactants raised to the power of the coefficient in the balanced equation. So hydrogen cubed times nitrogen to the first over ammonia squared. Now the concentrations are moles per liter. So rather than doing them in a separate step, I'm just doing it all at once. So we calculate the molarity of the hydrogen, moles per liter, and cube it. Find the molarity of the nitrogen, moles per liter. Divide that by the molarity of the ammonia, moles per liter, squared. That would give us Q, non-equilibrium values. We take the ln of that number, multiply it by the temperature in Kelvin, multiply it by 8.314 joules per mole Kelvin, take all of that and add it to 33 times 10 to the third joules per mole Kelvin. And what that gives us is the free energy change associated with this reaction at these non-standard conditions. And the value is negative, which means at these conditions, this reaction would be spontaneous. But at standard conditions, the value is positive and it would not be spontaneous. Relating free energy and equilibrium. Okay, well, if we're at equilibrium, the free energy of the products equals the free energy of the reactants. Everything's at its lowest possible energy. So delta G equals 0 at equilibrium. So if we look at our equation and we're at equilibrium, delta G here will equal 0. And if we're at equilibrium, Q will equal K. So we're going to get a slightly different equation here. This equals 0. So we're going to subtract RT-ln of K from both sides to calculate what our free energy change would be at standard conditions. So delta G naught would equal negative RT-ln of K because we're at equilibrium. So if we're at equilibrium, delta G equals 0, Q equals K, and now we have a new equation. And we could manipulate that equation if we wanted to calculate the equilibrium constants instead of the free energy change. We would just take E to the negative delta G over RT. So in other words, we divide by negative RT on both sides. That would give us the natural log of K. And then we take E to the negative on both sides of the equation, and that gives us this equation here. So if we want to calculate delta G, free energy from K, we would use this equation. If we wanted to calculate K from our free energy, we would use this equation. What does that all mean? Well, if K is greater than 1, products are larger than reactants. And it means that the forward reaction is spontaneous, so delta G would be negative. If K is less than 1, the reactants are favored. We don't have much product, which means the forward reaction rate is non-spontaneous, or delta G would be a positive value. And if K were to equal 1, delta G would equal 0, and reactants and products are comparatively abundant.